Welcome to our community service project on how computers work. I'm Elder Stanley, a missionary for the Church of Jesus Christ of Latter-day Saints.
Hi, I'm Austin Kellum. I'm a co-host and student here of Elder Stanley.
This is the first in a series, a 4-episode series. This one's called How Computers Do Math. Oh, I guess this is our first PowerPoint slide and we were on the second one already, sorry. But anyway, this is how computers work, the first section, how computers do math. This will actually be a 4-part series. The first one is the math, the second one is digital logic. The third one will look at a 4-instruction computer that I've designed and built, a CPU. It's got 4 instructions, so it makes it simpler to understand how the computer works and decodes and processes instructions. And then the fourth section will be how you program machine language for that little 4-instruction computer. Why do we use binary computers? This chart was to kind of help show that if you have a circuit that just is on and off like a light switch, that's a really simple circuit. It just has to make contact, break contact, make contact, break contact. If you have a circuit that's continuously varying like a light dimmer, then that's a lot more complicated circuit. And so if we can just do ons and offs, then we can make the logic, the electronics simple. It also makes the mathematics simple. For example, in addition, the only addition facts we have in a digital computer, 1 plus 1 is 1, 0, or 2. 1 plus 0 is 1. 0 plus 1 is 1, 0 plus 0 is 0. When we do multiplication, 1 times 1 is 1, 1 times 0 is 0, 0 times 1 is 0, 0 times 0 is 0. Really simple. When I was a kid in school, we had to memorize all the 100 times tables, and I remember I really struggled with some of them, like 6 times 7. I had to say, 6 times 6 is 36 plus another 6, 42. Anyway, if I just had to do this binary math, I would have been a lot happier in 5th grade, I know that. Anyway, so computers do math that way. What we want to do is have switches. Digital, switch like this, light switch, I don't know how many times a second can you flip that?
Not very fast.
Yeah, maybe 2 or 3 times a second, right? I've got here some examples of switches that we've used in the history of computers. The first one down here in the lower corner, this is called a relay. What the relay uses is a electromagnet to switch a switch right here. So I turn on the magnet, the relay gets pulled down, makes contact. I remove the current from the magnet, the relay comes back up. You can build switches that way, electronic switches, but they're not a whole lot faster than that. If I really optimize a relay, I might get it to switch maybe 100 times a second, but that would be a really optimized one. It's hard to get it to flip very fast. And it takes a lot of power to work the magnets. But anyway, some of the very first computers were built with relays. In fact, there's a story about the first computer was owned by the Navy. Had a bunch of relays in it. One of the people that worked there, a woman named Gracie Hooper, talked about how one day they came in, the computer was not working. They looked around through the computer and they found a moth had died and its wing was stuck between the relay contacts, so the relay couldn't make contact. And so they got a pair of tweezers, they pulled the moth out, they taped it in the logbook, and they said, "Bug found in computer." We don't really usually have insects in computers nowadays, but we still talk about bugs in software that started from that experience. One of the next kinds of electronic switches, what these are is switches. We can't switch really fast as fast as we want. If it's humans doing it, we've got to do it electronically. So we had the relay. The next really fast switch is a vacuum tube. These can switch 1 billion times a second. But the trouble with vacuum tubes is they're big, they take a lot of power, they take high voltage. Some of the very first computers used vacuum tubes too, but they weren't very reliable. They would tend to burn out. and then you'd have to replace them. The big breakthrough was in 1947. Some people at AT&T Bell Labs invented the transistor in 1947. Transistor is a little electronic device, can be quite small, and it works on battery voltages. It doesn't have to have the high voltages the vacuum tube needed, and it's a lot more energy efficient. So the transistor was a real breakthrough in how we can do, build devices that switch, and in fact, analog devices too. The next big, huge breakthrough was Jack Kelby and Robert Noyce invented what's called the integrated circuit, where you actually take a bunch of transistors and put them on a silicon chip. And in that way, you can have hundreds, thousands, millions. Nowadays, we have billions of transistors on one little piece of silicon. I've actually got some examples of some of those here. Let's see, do I have that? Here's a CPU example. This is an older Pentium processor, but there's just millions of transistors on each of those integrated circuits down here. So this is a CPU. Down here is a memory circuit. We're going to learn about memories and CPU, but that's an example of what some of those devices are. So anyway, that's the big breakthrough, integrated circuits. When we make numbers in binary, we're using digits that are 0 or 1, unlike decimal where we have digits 0 through 9. When we have a number that's in decimal, we multiply each digit by 10 to some power. So the digit on the rightmost is multiplied by 10 to the 0 power, which is 1. The second digit's multiplied by 10 to the first power, or 10. The second digit's multiplied by 10 to the second power, which is 100. So if we have a number like 1, 2, 3, that's 123. We multiply the 100 by, the 1 by 100, the 2 by 10, the 3 by 1. And that's how we make our numbers in decimal. Each digit's a multiple of 10. When we do a number in binary, the values are successive multiples of 2. So in each position, there are 2 possible digits, 1 or a 0. When we count, we start counting 0, 1, and then the next one would be, we can't put a 2, so we have a 0, 1, carry 1, so we've got a 1 in the next column, that's worth 2, and a 0, so, and then the next digit would be 1 plus 2, which is 3, and then we go to 4, 5. Let me show you a little binary counter just for fun. So here's the little binary counter that shows you what numbers look like when we count in binary. So we're going to turn this thing on. We got it counting really fast right there. Let's slow it down. We'll slow it down to about 2 counts a second or something like that. So then you'll see it count, and let's clear it so we can see it count. So we starting with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Anyway, that's a binary count. Let's go back over here to our PowerPoint presentation. Have you seen this sign? Some people have t-shirts that'll say there's 10 kinds of people in the world, those that appreciate binary and those that don't. Have you ever seen one of those?
No, I have not.
Oh, okay. Anyway, what does that mean? If you say there's 10 kinds of people in the world, those that understand binary and those that don't, that doesn't make sense, because what are the other 8? But if you understand binary, when we count in binary, 0, 1, 2, so that's a 2 in binary. There's 2 kinds of people in the world, those that can appreciate 1 0 as a 2, and those that don't appreciate 1 0 as a 2. And so that's what those t-shirts are talking about. Binary uses a multiple of 2 for each value of each digit. So where in decimal it's like 1, 10, 100,000, 10,000, 100,000, million, 10 million, 100 million, billion. In binary, we have 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024. Anyway, they're all multiples of 2. Let's look at some stories here to talk a little bit about binary math. Here's a story about a farmer. He has a field that he wants to have plowed, and he has a gold chain that has 7 links. And he contracts with this guy, and he says, I'll plow for a whole day for 1 link out of your chain. You know, and so he's got 7 links. He can pay for a week's worth of plowing, which will finish his whole field. But the farmer doesn't want to give him the whole chain up front because he may not come back on Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday. So he wants to pay him each day, one at a time. You know, the guy doesn't want to wait and be paid when he's done, so they have to figure out a way to pay him every day. And the farmer goes to the blacksmith shop, and the blacksmith says, well, I'll cut your chain, but it's going to cost you half a link for each cut. And so you don't want to make very many cuts. So what's the minimum number of cuts he could make? And
just 1.
Yeah, just 1. If he goes in here and he cuts after the 3rd link, cuts that one in half, he can make his chain into a binary number system. So he has a 1, he has a 2, and he has a 4. So what does he do each day when he pays the farmer? At the end of the first day, he says, okay, here's the 1. Now you got a 1. Now you come back the second day and say, okay, give me that one, and you can have the 2. And then at the end of the 3rd day, I give him this one. So now he's got a 3. And then we come back at the 4th day, you give me those back, and here's the 4. And then he comes back the next day, and we pay him 5. And then the next day we say, okay, give that one back. And now you got 6. And then at the end of the next day, we give him the last link. And we haven't had to cut the chain a lot. We haven't had to trust each other. And we've been able to use a binary system to you know, make numbers from 0 to 7 with binary digits of 1, 2, and 4. It's another story I wanted to tell that just illustrates how binary math works. This is called the grains of rice on the chessboard story. There was once a guy who saved the king's life. And the king says, you can have whatever you want, up to half my kingdom. And the guy says, oh, king, I don't want much. How about 1 grain of rice for the first square on a chessboard, and 2 grains of rice for the second square on the chessboard, and 4 for the next one, and 8 for the next one, and 16 for the next one, and so forth for the 64 squares on a chessboard. King says, oh, you know, we got to give you more than that. Guy says, no, that's fine. Just give me the grains of rice. So the king got out his mathematicians, and they calculated out how much rice that would be. Well, it turns out it's this number right there. If you multiply 2 to the 64 power, you get a number like 18 quintillion. It turns out there's not enough rice in the whole world to pay that debt. And so the king was really embarrassed. I think you'll read on the internet 2 versions of the story. One where the king chops the guy's head off because he's so embarrassed. Not a very satisfying answer. The other one where he says, here, marry my daughter, become the new king when I retire. That's probably a little more satisfying conclusion. Anyway, let's do one more example of counting in binary. Let's talk about, here's a little calculator you can use and maybe try to put it so that people can see it. Let's say we want to buy a bicycle. Oh, let's look at our binary money first. So if we had binary money, in the U.S. currency system, we actually have a narrow range where we actually have binary currency. If you have a $1 bill, that'd be a 1, like the 1 link on the chain. We have a $2 bill. If you go the other way, we could have, you know, we have a 50-cent piece, half of a $1 bill. and we have a 25-cent piece, which is half of a 50-cent piece. So in that range, our number system is actually binary. If we had an eighth of a dollar coin, and if we had a $4 bill and an $8 bill and a $16 bill and a $32 bill and a $64 bill and a $128 bill, we would have a binary currency. What would be the advantage of having a binary currency? Well, in your wallet, you'd never have to have more than one of each thing to buy anything. And so let's see how that would work. Let's say we want to buy a bicycle, and the bicycle costs $231.75. So you can put that in a calculator if you want. So we got $231.75 is how much our bike costs. Let's see what we would have to do if we were buying that in binary. So let's see if we can figure out how many $128 bills we'd need, and how many $64 bills we'd need, and how many $32 bills we'd need, and 16, and 8, and 4, 2, 1, and we'll put a half and a fourth. We didn't really leave quite room for those, but 1/2 and 1/4. Okay, so if we're buying a bike that costs $231.75, we'll take out 128, one of those. How much do we have left?
We have 103.75 cents.
Okay, so we can take out a 64, right? So you take out a 64, now what's left?
$39.75.
Okay, so we can take out a 32, right?
$7.75.
So we don't have enough money here to get a 16 or an 8. We're down to $7, but we can take out a 4, right?
$3.75.
Okay, we can take out a 2 from that.
$1.75.
Okay, we can take out a 1 from that. How many halves?
75 cents.
Yeah, so we can take out 1/2 and 1/75. So that's what our binary number would look like to buy that bicycle. We'll talk about it again a little bit more later on, but anyway, that's an example of a binary value. Do you wish we bought our money bought our things that way?
I don't know.
Anyway, usually the computer, we actually work in decimal, and the computer translates for us. But fundamentally, in the computer, it does everything in binary. Okay, let's just leave this down here for a second. Okay, here's an example of I guess, did we see the binary counter? We saw the binary counter, right?
Yep.
So let's go back over here. So here's our binary counter that we were watching, still counting. What we're going to do is look at how what that would look like in decimal. So here's a counter that shows binary and the decimal values that correspond to it. So let's start this one counting. Let's enable our counter. Okay, I guess it's counting really fast too. Let's slow this one down too. So we'll slow it down to like 4 counts a second, and let's reset it again too. So we're going to start with 1, 3, 4, 5. So you can see the binary on top and the decimal on the bottom. So this is showing how we count in binary, and what the equivalent would be in decimal. We can make huge numbers in binary, like the 2 to the 64, the 16 quintillion, 64 or 128-bit numbers. We actually use those in our computers now. But anyway, huge numbers we can make with binary, but we have to have lots of digits. Okay, let's go back over here to our PowerPoint presentation. So one of the things that we do if we want to have a big number, like a 64-bit number, we want to display it easier for human beings. We could put it into a decimal number, but decimal is not an even multiple of a binary number system. One of the things that we can do that makes converting from binary to another system that's easier for humans to understand is to break binary numbers into 4-bit digits we call nibbles. And each of those nibbles we can assign a hexadecimal value. Those hexadecimal values go from 0 to FF. If we count in binary, we'll see here we go 1, 2, 3, 4, 5, 6, 7, 8, 9. But we've still got lots of digits that we could make with our nibble. So what we do in hexadecimal is we want to have just a 1-digit number represent each nibble. So we say, okay, this is an A, a B, a C, a D, a E, and an F. So 1111 is F. And then if we add 1 to that, we're going to now have 0, 0, 0, and we're going to carry to the next place. So we use that for hexadecimal. If we want to convert a number from binary into hexadecimal, we just use this table and we can convert our number. So if we wanted to convert this number to hexadecimal value, let's just erase this down here. What we would need to do is divide it up into chunks of 4 and then look up the hexadecimal values. Now it turns out we need to have a binary point right here, not a decimal point. And so here we've got 1, 1. It would be 0 eighths and 0 16ths. So that would be 1, 1, 0, 0. That would be a C. So we'd have a C for that digit. And then we're going to come over here. 1, 2, 3, 4, right here, 4 digits. 1 nibble right here. This is 0, 1, 1, 1.
7.
So that's a 7. Yeah, okay. And then this other one is 0, 1, 1, 1.
E.
So that's an E. So if we were to write this price out in hexadecimal, we'd say $E7.C. So I don't know if that looks like it helps, but instead of having like a 64-bit binary number or a 128-bit binary number, we can break it down 1/4 the size by using hexadecimal numbers. So here's our bicycle price up there on the top. We need to add extra zeros on the front and the end if we need to make groups of 4. And then we replace each group with its hexadecimal character, and so we get the $E7C. Okay, here's our binary counter with hexadecimal on there. Let's look at this work. Okay, we'll start this one going, and then you can see, we'll slow it down to, let's make it 4 hertz. We'll enable it right here. We'll turn this on right here. Now you can see it counting in hexadecimal. You can see hexadecimal makes that even block of 4 digits, where decimal takes 3 digits to express 8 binary digits, a byte. Hexadecimal just takes 2 digits.
Interesting.
So anyway, I think that's really about what we've got for our presentation for today. Let's go to back to our PowerPoint presentation. So next time we'll see computer logic. Anything you'd like to ask about?
Not really.
Okay.